place where I stopped last time, and my purpose in these lectures is to kind of outline the main setup of circle method, not to go to too much details. And I was remarked, now I can better recall it, that, I was remarked on Tuesday at the end, that the theorem of Birch, general as it is, already for cubic forms gives a non-trivial results, namely when you take d equals 3, then you get that at least non-singular cubic form of at least 17 variables represents 0 non-trivially. At the beginning of his paper, Birch writes that he was inspired by the previous work of Davenport, in which he proved that any cubic form of 32 variables non-trivially represents 0 without assumption of this form being non-singular. Just after the paper of Birch was published, Davenport published a new paper where he proved that a cubic form of at least 16 variables represent 0 non-trivially, and that's the best result up to now. But sometime later, trying to improve on this result, sometime it means 20 years after that, Brown proved the following theorem, that any cubic form, any non-singular cubic form of at least 10 variables also represents 0 non-trivially. And by non-singular cubic form, I mean the form, such a form for which this gradient of the form, that's all its partial derivative, do not vanish outside of the origin, or if you wish, if you consider the projective hypersurface defined by the equation Fa equals 0, then it means simply that this hypersurface is not non-singular. My purpose is to outline the proof of Brown theorem, which is necessarily rather technical and which uses Deline's estimate of trigonometric sums, which were, of course, not available at the time Davenport and Birch wrote on this subject. So I will start by introducing some notations. So let fx be written in this form. It's a cubic form. So I assume that the coefficients c sub I yod k are symmetric in the indices. And also then, okay, so it's and also, so the first lemma with Brown proofs, it's a relatively simple lemma that one can choose a point x0, just a real point, such that which lies on this hypersurface, which is non-singular, and such that rank of this matrix defined above is at least n minus 1, where n is the number of variables. Having fixed such a point, one defines a weight wx and an exponential sum s alpha wx exponential e alpha fx. And here one chooses a big number which is going eventually to infinity p, and denotes by p0 by p sub 0 p divided by log p squared. So having done that, one remarks that an integral, again, from over an interval of length x gives you just the sum of weight omega x over all the integer points on this hypersurface. And now you see that the first difference compared to what we were doing, instead of counting points in the box, one gets an exponentially decreasing weight. One counts them with this weight, so this sum is, of course, absolutely convergent. And if one wants to, so instead of getting an asymptotic formula for the number of points, one gets a formula for I'll use this convention. One gets a formula for this sum, and of course, if this sum goes to infinity as p goes to infinity, then of course there are non-trivial points, because points at 0 will contribute just one term to this form, to this sum. To treat this sum, one uses a different method, a new form of the circle method, which was invented by Klosterman in the paper in 26, and that's the first paper in which Klosterman sums actually appeared. So this paper was about representations of integers by quaternary quadratic forms. So this new form of the circle method goes as following. There is another reference to this. There is a paper of His-Brown, which everybody who wants to understand the application of circle method to counting rational points should read. That's a paper of His-Brown in 1996 on the new form of a circle method, where he actually treats the quadratic forms, but says that later he probably applies these things to cubic forms. I don't think he did it, but at any rate, the ideas behind this method are described in some details. And for instance, it is a formidable problem. Well, I once tried it, but couldn't do. I mean, to count points on the quaternary quadric, on the quadric given by quaternary quadratic form, indefinite, it's there one has to sum Klosterman sums, and for that one needs special techniques. So this paper is highly recommended, but I just described the method of Klosterman. So one chooses some number q, which is approximately p integer, which is approximately p to the power 3/2. And one chooses x to be minus 1 over q plus 1. And one divides this interval according to what is called Fourier dissections. I'm not sure that nowadays everybody knows what it is, but it's just, you can just, if one just orders all the numbers, orders all the rational numbers in this interval by increasing order, yes, then what is one obtains what is called Fourier dissections. So you just take all the rational numbers with co-prime numerator and denominator and arrange them in increasing order, and denominator shouldn't be bigger than q. Then it can be shown easily that the numerators and denominators satisfy the relations as above. And one, instead of speaking of major and minor arcs, one just considers the intervals between these rational numbers and write an integral as an integral over this rational number, over these intervals. So if you do that, then you get such, then you express, to do that means to expressing this integral as this sum, where the interval one integrates over is given as following here. Now one introduces a new exponential sum, and I will use an abbreviation e sub q beta. It's just e to the power 2pi beta divided by q. And then after some calculations, yes? I beg your pardon, I didn't get it. What is bigger?
R double prime over Q double prime is larger than R over Q.
No, if you look at it, then you will see that it's, I think, is it? Oh, so it's in one, so once, oh, I overdid it, sorry. One should be certainly plus one, yes, you are, thank you. So after some calculations, one obtains the following formula. When I say after some calculations, it doesn't mean that I offer you this calculation as an exercise because, well, that's part of the method, but I can't go into details. After some calculations, Brown obtains from the previous formula, from this formula above, this formula above simplifies to this formula, where CUQ is the maximum of this sum over the interval over this interval. And now, to this sum, to the inner sum, the Poisson summation formula is applied, not an adelic, but just a usual Poisson summation formula from analysis. And then then this expression becomes more tractable. Namely, you see, one can rewrite this sum as a double sum as following, as above, and then one has an inner sum over lattice point in Zn, and to this inner sum, one may apply the Poisson summation formula going over to the Fourier transform of this, going over to the Fourier transform of the corresponding function. And after applying this and doing again some calculations, one reduces this formula, one obtains the following result for S sub u q z, where this E0 z beta is some integral over this weight Wt, and where moreover, one gets an estimate at the same time, an upper bound for this E0 sub p. And now, with these expressions at hand, one applies the estimate of Deligne, which is a direct consequence of his proof of Weil conjectures, namely, of course, a more general estimate holds, but one applies just this estimate for the prime field of P elements. So, psi H and E are two. H is a non-singular form of degree D, and here non-singularity is used. And E is some additional term, additional polynomial of degree smaller than D. And then, if one applies this formula, then one gets a bound. Then one can get a satisfactory bound, upper bound, for S0 QZ, for S0 QZ, not only for prime Q, but also for SUQZ, sorry, not only for prime Q, but also for any square-free integer Q, because these sums, kind of generalized Clusterman sums, enjoy multiplicativity. You know, if you take I and S relatively prime, then one can factor out these sums. And so one gets the upper bounds for these sums S UQA for square-free Q. When Q is not square-free, but then every number can be written as a square-free part times a square-full part. That's the part which is divisible, in which no primes comes in the degree smaller than 2. So if one does that, then it suffices to also to consider sums over square-full for square-full Q. And that His-Brown does by some elementary, also rather imaginative arguments. And in this case, one doesn't obtain a bound for an individual sum S sub U Q A, but estimates them on average. And when one combines these estimates with the formula we already have, which we already obtained for the integral EP, then one obtains an asymptotic formula for this integral where E1p is some what is called the singular integral, and sigma is the singular series. Now, this singular series converges absolutely, And actually, it was already investigated in the papers of Davenport, in the first paper on 32 variables, on a representation of 0 by cubic forms with depending on at least 32 variables. And Davenport proves that it's positive, this series, sigma, and doesn't depend on p. And for integral, well, one can just estimate this integral, and it's of right order of magnitude, and then sigma is just of order 1, bounded from above and below by some absolute constant, and therefore one obtains the result that P goes to infinity as P goes to infinity. Now, this machinery, I mean, projectors, make one much quicker, because originally I wanted to stop at this point, but now I've foreseen that I have more time, so I will continue. But first, let me mention that in a subsequent series of work, Hooley, building on the work of Brown, extended his results to form of 9 variables. And he proved for non-singular cubic forms of 9 variables Hasse-Minkowski principle. For 10 variables, we don't speak about Hasse-Minkowski principle because the periodic conditions for a cubic form of at least 10 variables are automatically satisfied. But that's not the real conditions always satisfied because it's of odd degree. But for 9 variables, it's not true. And there, Hooley proves the Hasse-Minkowski principle, that is, that the form represents 0 non-trivially if it represents its non-trivially in every periodic field. And it is interesting to remark that in the first paper in this series, no asymptotic formula is obtained, but rather obtained a pure existence theorem. And one may wonder how it is possible with the machinery of the circle method. And the reason is that the argument is kind of divided in 2 parts. Forms are divided in 2 classes. For one class of forms, circle method is applied, and then one obtains an asymptotic formula. And for the other class of forms, one obtains an existence theorem. And this division into classes is also not quite constructive. So in the paper of Hooley, he uses even a more sophisticated version of the circle method. He averages over several dissections, Fourier dissections, and that allows him to incorporate some more advanced estimates of the geometric sums which follow from Deline's theorems and which were obtained in later work by Katz. And in subsequent papers, Hooley, first of all, allows some isolated singularities, and secondly, he also changes his method, so he obtains a kind of asymptotic formula, or at least an estimate of the right order of magnitude. So those are rather technical papers, and I didn't intend to comment on them any further, so here one offers exercises, but it's rather, if someone of you is interested, so one can organize a seminar and try to study these papers of Brown and Hooley. And there is also another problem, try to do analogous things over number fields. It's absolutely open. So then I will comment later on at the very end of the situation about circle method over number fields, briefly. So let me now return to the Birch's theorem, and I'll start by telling you about about a lemma which we proved with Alexander Grigorievich Alexandrov, because I don't think I talked about it outside of Bonn, and Alexandrov is somewhere in Moscow, so probably it is. So that's a purely algebraic result, and I will just state it as an algebraic result, and after that I will be able to continue with my considerations of Birch's theorem, because it's the only general theorem in this field. So let K be a perfect field. Well, since it's algebraic, we formulate it in some generality, but my application is simply to Q, and so you can assume that K is, say, a finite field or a field of characteristic 0, but it holds, if we are not mistaken, in this generality. So I'll consider a perfect field. I'll consider a system of homogeneous non-constant polynomials, f sub j x, and I will consider sequences of numbers in this field K, and ideals. I want to consider algebraic set defined by the equations f sub j x equals mu sub j, but here I need to be a little bit more precise. So let me assume from the very beginning that n is bigger than r. Let me determine and I define an ideal up sub mu, and for mu equals 0, just omit the notation and define it by a. And then let me define the ideal which defines the singularity of this map, namely ideal generated by the minus of maximal order here. And then I also consider an ideal D, which is an intersection of these ideals. A sub mu j is a sum of ideals, the ideal generated by them, and I take this intersection. And let me consider three affine scheme, one defined by ideal A, another, well, that's a particular case of this V sub mu, defined by ideal A sub mu, and let W be the affine scheme which is defined by ideal G. Now let V star denote the Zariski closure of this union of singular parts of V sub mu. So then we proved a few years ago the following theorem. So assuming that V is a complete intersection, that its dimension is equal to the number of variables minus the number of equations, one can prove that then V star is determined by this ideal D, and this ideal D lies between ideal J and its radical. You see, these varieties not necessarily reduce these schemes. So the ideal J may have so to say 0 divisors. And from this theorem as an immediate corollary, I obtain that this set, that is the set which occurs in the papers of Birch. And W is the set which he can handle. And he just identifies it. At that time, at the early 60s, the language of schemes was just only in the process of developing, and that's, if you wish, also a research exercise to rewrite this paper of Birch in modern language that hasn't been done. And Birch just identifies these sets without speaking about the risky closure. And the motivation of this paper was that I was trying to find a counterexample to his statement, and then together with Alexander we actually proved that, as one says, it's morally correct. So one sees that the set V star is homeomorphic to W. In particular, they have the same dimensions, and moreover, they have the same set of key points. So that more or less justifies the assumption of Birch. And I think the only mathematician who noticed it, at least in press, was Wolfgang Schmidt. He doesn't remark on that, but he just in formulation of Birch's theorem, instead of using V star, uses this set W. So having said that, I can now return to the paper of Birch, and I would like to say a few words about his argument. I mean, as I said, it would be nice if it is rewritten in modern language. Skinner kind of tried to do it, and Schmidt, but I'm not sure that well, they use some different language from, well, I'm not sure that it is really done. Or to put it hasn't been done to my satisfaction, let me put it like this. So now I take K equals Q, so it's certainly a perfect field. I will assume that these forms are, have integral rational coefficients, just cleaning the denominators. I will assume from the outset that the dimension of that V is a complete intersection, and I will denote by delta F the common dimension of V star and W. In my previous lecture, that was just the dimension of W. And moreover, I will assume that all these forms are of the same degree. I already assumed it when I formulated this theorem on Tuesday. So D is the common degree of all these forms. I suppose that, I repeat again that it's a complete intersection, and suppose that Birch's inequality holds. Then the conclusion is the following, that if there are non-singular points for every local field, for R and for QP, for every P, then there is a non-trivial point, then this form is non-trivially represents 0. In fact, of course, Birch proves much more than that. He obtains a certain asymptotic formula, and not only for this variety V, but also for the variety V sub mu for mu rational, for mu integral. But that will become clear after this very brief sketch of his argument. So one defines, as usual, that's the standard circle method of Hardy and Littlewood. One chooses two numbers, P, which is going eventually to infinity, and theta between 0 and 1. At those years in the 60s, the theta was always between 0 and 1. I remember writing it, it was just taken for granted. And so with these two parameters, one defines the Major's arc acts M sub A Q. So A is a certain sequence of natural number. Q is, of course, a natural number. And then I'll remind you that we had an odd-dimensional torus. And the major arcs are just a union of all these special arcs, where you should take notice of the condition. It is not assumed that every A sub j is co-prime to Q, but only that all these R plus 1 numbers are relatively co-prime, and then the minor arcs are torus minus the complement of the major arc in this torus. Then one chooses a box in Rn with side lengths at most 1, and for every integral vector nu, one considers the number of points, of integral points on this variety v sub nu, which lie in this box. So this v sub nu, I remind, is just given by the equations f sub j x equals nu, fjx equals nu j. So that's the starting point. Then probably one of the key observations is a certain geometric condition. To explain this condition, I have to go through some further notations, because it is difficult to talk about these things without writing formulae. I mean, in an invariant way. So I introduced again this sum, but now, as compared to later work of Heath, Brown, and Cooley, it's just a sum of the finite sum of integer points in this box, gammatically extended box B, P times B, and then it is immediate that the number of points n p nu is just an integral over the torus of this weight, and it breaks down into the integral over major arc plus the integral over minor arcs. And now one has to go, one writes down the coefficients of all these forms, A with the upper index I, assuming that these coefficients are symmetric in the suffixes. And you see I wrote here, following Birch's notation, J sub 0, because these first index are treated in a special way. One defines a multilinear form, psi sub ki, in such a way replacing this first index by k, summing over other indices, and here there are z different variables. Here it's 1x. And one then considers the algebraic set, which just as I already did in our, when discussing this theorem with Alexander, the set which is defined by the principal minus of this matrix, namely, so that's an algebraic set in a affine algebraic set in A to the power n subscheme of affine space of dimension n times d minus 1. That's how many variables you have here. And then comes, so the first lemma is that the dimension of this set is not bigger than delta f plus n times d minus 1. And Birch's argument is he just goes over to complex points, and it's some geometric argument. Now, the geometric lemma is the following. Probably that was the main invention. I mean, it certainly didn't talk you probably before. So for alpha in the minor arc, we either have an estimate, an upper bound for this sum, the geometric sum, W0 alpha, or else the dimension of this set U is bounded from below. But the second condition is being eliminated with the help of lemma 1 and this bound which we imposed on n. Delta f is smaller than n minus this product, and dimension of U is smaller than delta f, so one can bound it. And then it follows that a bound, then one obtains a bound, a satisfactory bound of the integral over a minor arcs. The treatment of major arcs I shall not describe here. I'll just state the result, and it's also a non-trivial thing. I mean, and here the most difficulties are being presented by the singular integral. Singular series are kind of being evaluated routinely. But one arrives at the same conclusion at which we arrived when I described the general circle method, namely that if there are periodic points non-singular for every nu, if for some nu there are non-singular periodic numbers, then I get sigma nu bounded from below. And if there are non-singular real points, say in B, because we are counting in B, then we get that mu infinity nu is at least 1. And when we combine it with the asymptotic formula, which I somewhere wrote, but which I still have, I think. Just a second. It's number 20. So if we substitute that in the asymptotic formula we had, then we see that actually one obtains here not simply an existence of point, but an asymptotic formula for an asymptotic formula for the number p of points on this variety defined by these numbers nu by equating the forms f to nu. Okay, I don't know if I will be able to find this slide again, probably not now. So I will stop the discussion of this thing here, of Birch's theorem, and let me now comment, as I promised, on the generalization of the circle method to number fields. Let me say that, as I already mentioned at the beginning, the circle method was not designed to treat Diophantine equations over to treat rational points of varieties defined over a number fields. And Ziegel probably was one of the first who tried to generalize methods, to try to use methods of analytic number theory in number field setting. Now, the first, after the paper of Birch appears and of Davenport, there was an important paper by Ramanujan where he proved that a cubic form of sufficiently many variables over a number field has a non-trivial rational points in this number field. A definite exposition was given by Pleasance, who generalized this, the 16 variable Davenport, the 16 variables Davenport theorem to number fields. And that is actually, from my point of view, that's the only, well, he refers to the previous authors, in particular to Ramanujan and to some other authors, but he sets up the whole machinery and surprisingly obtains the same result as Davenport. Now Skinner, the goal of Skinner's paper is to obtain an analog of Birch's theorem. Already in the paper of Birch, at the end, it is discussed the question of generalizing to number fields, but he kind of used standard argument, at that time probably not so standard. He refers to the, at that time, recent work of Andy Weil about algebraic groups and adels. So there is a base change. You know, you can rewrite any equation with coefficients in number field as a system of equations over rationals and then variables you can also re-express. And in this way, one can generalize Birch's results to number fields, but the dimension of the co-dimension of the singular locus is huge compared to the degree of the equation. Skinner thus generalizes Birch's work to the number fields, getting more or less the same inequalities as in the original paper of Birch. And the whole field seems to deserve a certain survey, and I was told that it will be probably done by those people who still investigate the applications of circle method. But I can mention it to you as a kind of research. As a kind of research exercise, if you would like to do it. So let me stop here.